Welcome to this deep dive into Gravwell performance tuning, titled The Need for Speed. We will focus on optimization protocols to enhance your cluster's performance. Like a high-performance race car, Gravwell requires precision tuning across 3 distinct layers to handle enterprise-scale data loads: query tuning, indexer tuning, and ingester tuning. Gravwell is designed to push your disk, network, and CPU. Tuning prevents bottlenecks. Our optimization blueprint focuses on 3 key areas: query efficiency, indexer storage knobs, and ingester edge agent optimization. We begin with Phase 1, query tuning. The first place for performance gains isn't a config file, it's right in your search bar. Gravwell uses a pipeline concept. Queries are processed linearly from left to right. Each module, like grep, JSON, or stats, acts as a filter or modifier. The sequence dictates the computational cost. The golden rule is to filter early. Narrowing the data aperture early reduces memory consumption and CPU cycles for the entire search duration. Less data equals more speed. Compare an inefficient syntax, like tag equals star pipe grep, bar, which reads every tag and is slow, with an optimized syntax, like tag equals JSON data, JSON foo equals bar, which targets only the relevant data well. Benchmarks show orders of magnitude improvement when utilizing proper filtering and acceleration hints. Moving from a raw full-scan search to an accelerated search significantly reduces the number of entries processed. Phase 2 is acceleration. This involves moving from manual scanning to indexed high-speed retrieval. By default, Gravwell scans data. Acceleration creates a, quote, cheat sheet side index of all text fragments. The system instantly identifies specific locations of terms, reading only relevant entries from disk. Enable acceleration by editing gravwell.conf and specifying accelerator name equals full text in the storage configuration block. This reduces disk I/O, enabling high concurrency sub-second searches. Parallel processing for modules like JSON and grep happens on indexers. Calculations, such as stats or table, occur on the web server. Condense modules to the right to maximize parallel work. Phase 3 focuses on indexer tuning. This involves configuring the storage engine for maximum throughput. For storage optimization, point search, scratch, and render store to your fastest storage, such as NVMe or SSD. This handles temporary files when results exceed RAM, preventing system contention. In memory management, the pipeline buffer controls data blocks between modules. Increasing buffers uses more RAM and risks out of memory, or OOM, crashes. Adjust these settings carefully. The pre-buffer space is where Gravwell organizes incoming data before committing to disk. High-throughput systems benefit from larger target blocks, like 8 megabytes, for better I/O efficiency. Pre-buff parameters include pre-buff max size for total RAM, pre-buff max set for handling time jitter, and pre-buff tick interval as a safety timer for disk commit. Phase 4 is OS and kernel tuning, which aligns the Linux kernel with Gravwell's architectural requirements. For compression and file systems, use BTRFS transparent compression instead of user mode compression. This operates in the kernel, enables memory deduplication, and reduces CPU overhead. Tune the Linux kernel's vm.max_map_count to 300,000 or higher. Gravwell extensively uses mmap, and the default limit is too low for busy indexers. Failing to increase this causes cryptic OOM errors. Phase 5 focuses on ingester tuning, optimizing the agents at the edge of your network. To handle bursty ingest, configure cache mode equals always. This uses the local disk buffer as an absorber, preventing data loss when bursts exceed network throughput. Specific ingester tips include increasing Kafka batch size for higher throughput, tuning max files watched for the file follower, and using BPF filters and SnapBlend for net capture. Phase 6 addresses throttling, ensuring system stability through controlled slowdown. Tuning is a balance between RAM and speed, and throughput and reliability. Remember to filter early, check indexer buffers, and increase kernel map limits to optimize your cluster.